Third one, solution and qualitative properties again. Now in solution and colligative property, third colligative property, which is depression of freezing point. Now in depression of freezing point, the temperature at which solid liquid phase are in equilibrium. The temperature at which solid and liquid phase are equilibrium. Are in equilibrium. Is known as freezing point. Or FP, short introduction. Okay. So basically, freezing point, we can write temperature at which vapor pressure of solid becomes equal to vapor pressure of liquid. So the temperature at which vapor pressure of solid becomes equals to vapor pressure of liquid. Now at freezing point stuff, we can write water solid and water vapor both are in equilibrium. Okay. So in this case, del H value, del H, which is the endothermic process, del H value which is positive, endothermic process. Okay. Now look, when you heated anything, heating stuff, when temperature greater than T1, we can say solid converted. Heating means temperature, that means T1 is the initial temperature. Now you are heating. This one is the final temperature. So final temperature is basically, it is definitely greater than or equals to boiling point. So in this case, this stuff, solid freezing point, solid converted to liquid. So here, when solid converted to heating means when solid converted to liquid, when you heat it, basically solid and liquid, water which is in ice and water in liquid state, they are in equilibrium. Now when you heating some substance, when you heating H2O, so what is happening? Amount, so you can say after heating, the liquid amount increases, H2O amount increases. Okay, after heating. Now when you cooling all the thing, that means temperature less than T1, then we can say liquid converted to solid, backward directions dominate, in this case forward direction, in this case backward direction, BD, backward direction. So here liquid converted to solid means ice amount increases. Is it clear? Write it down quickly. Writing completed. All of you. Next, vapor pressure and temperature stuff. Now, if you go through this one, vapor pressure and temperature. Here only solid and liquid you have to require. Gaseous stuff not required. This represents solid. This represents liquid. Now, when you vapor pressure and temperature relation, you know that what is the vapor pressure and temperature. Now, for volatile substance, if you go through the heat, it can easily get separated. So from here, if you write down, if you go to the previous class note, we all know that vapor pressure and boiling point both are inversely proportional. Okay. Now, for solid, this is for pure liquid. Now, if you add solution, solution means where solute substance are there with solvent. Now, when solute substance present in a solvent, we can say this becomes impure. This becomes impure. And due to impurity, vapor pressure decreases. So vapor pressure decreases. Okay. So if you draw a line, this is a freezing point, TF, no, freezing point. Freezing point at 0 degree centigrade. Or freezing point of pure liquid. And this one is the TF. TF is freezing point of solution. Point of solution. Okay, this is the freezing point of pure liquid. Now from here we can say definitely TF is less than TF now. So when you add some amount of solute, freezing point decreases. And this is called depression of freezing point. Freezing point. Okay. And the difference between these two, del TF, which is equals to TF naught minus T. Okay. Here TF value definitely less than TF value. Depression of freezing point. Okay. Is it clear? This is the first equation. Write it down on the start. Writing completed, all of you, quickly. Next, moving to the thermodynamics stuff. What is the thermodynamics? How can you prove this equation by thermodynamics? You know that for pure solvent, this is S of pure solvent, which represent entropy of pure solvent. Okay. This one represent entropy of pure solvent. Now, solute when added with solvent, it becomes solution, and S of solution, which represent entropy of solution. Okay, and one thing just remember, S of solution, entropy of solution always greater than entropy of solvent. That means pure. Okay, and entropy of solid is least. Entropy of solid, which is least. Least. Now, suppose if you draw the entropy stuff, S of solid, this one is the S of solvent, this one is the S of solution. Now, this difference we can write del S of solution. This one we can write del S of solvent. Now, when solid converted to liquid, heat required. This heat is called heat of fusion. Okay. So, S of entropy, S of fusion, which is equals to del H of fusion. This temperature, which is a freezing point. Okay. Okay. This temperature, which is called freezing point. Now remember, if this value increases, in which case this value is high? Definitely this case. If this value increases, this one and temperature, which is inversely proportional. Now check this one, del S value, in which case is high. This value is fixed, because fusion case the value is fixed. Now del S value is high for solution. If this value is high for solution case, temperature of solution is least. If this value is low for pure solvent case, then T naught value is high. So that's why we can write T naught value always, T naught F value, which is always greater than 6. Write it down quickly. Okay, so according to thermodynamics, we can derive and you can prove this expression. Write it down. Writing completed. Next, another formula. The first formula is, we all know that TF, which is equals to TF naught minus. That is the first formula. To go through the next formula. Next formula is TF value. This is the first. TF value, del TF value, which is proportional to molar. So if you remove the proportional sign, del TF, which is equals to I into KF into M, where I represent, this is the second equation, I represent van der Waals constant, M represent molality, KF represents molar depression constant or gyroscopic constant. Gyroscopic constant. Okay. And Kf value of water, always remember Kf value of water, which is equals to 1.86 Kelvin kg per mole. Okay. And the last one, last formula. And this constant is for solvent. The last formula, Kf, which is equals to R into T naught F square into molar mass 1000 into kLH fusion. Similar like this. Last class, instead of Kf, this value is a Kb. Others, all the stuff are same. Okay. This M is molar mass of solvent. Remember, third equation. Okay. So what is R? R is UGC, universal gas constant. Generally, you can use 1.98 or 2 calorie in form of calorie, or you can eat 8.31 when you use joule. T naught F, which is freezing point for pure solvent. Point for pure solvent. Okay, M of solvent. Molar mass of solvent. Okay. Del H fusion. Heat of fusion. Okay. Write it down quickly. Okay, completed. Quickly write it down. Done. Next, question number 1. Try to solve it. Only 3 questions are there. Solve it. Calculate freezing point of a solution. So within this week, I will complete this chapter. Obtained by dissolving 28.4 gram of Na2SO4, having degree of dissociation 75% in 200 gram of H2O. Solve it, giving you 4 minutes time to try to solve it. Completed this one. Look, how can you solve this one? What is given? First of all, this one 75%. What is the degree of dissociation alpha? 75% means 75 by 100. That means 3 by 4. Okay. Now Na2SO4. What will be the molar mass? Molar mass is 142, where N value is 3. Why N value is 3? Because after dissociation it gives 2Na plus SO4 2 minus. Okay. Now what is the I value? 1 plus M minus 1 alpha. 1 plus 3 minus 1 alpha value is 3 by 4. That means 5 by 2. Now del TF, which is I into KF into M. I is 5 by 2, K value is 1.86, M is 28.4 by 142, 200 gram converted to kg, 1000, that is 4.65. Okay, so that is GLD. Now you have to find what? TF value. Now TF value, how can you find? We all know that this formula TF equals to TF naught minus TF. Now TF equals to, can I write this TF naught minus of del TF? So if this one is a 0 degree centigrade, 4.65, that means minus 4.65 degree centigrade. You can write down this one as a Kelvin. This is 268.35 Kelvin. Okay, any doubt? This is clear for all. This stuff is clear for all. Now moving to the next question. Another question. Calculate the amount of sodium chloride amount of NaCl which must be added. 1 kg of water so that the freezing point of the solution is depressed by 3 Kelvin. Okay. Kf value 1.86 Kelvin kg per mole solid. completed. Look, how can you solve? First of all, NaCl will dissociate. What is happening? Na plus Cl minus, that you know that. Now first find out the Van't factor. Van't factor is 2. Okay. Now find out weight Wb del Tb into Mb into Wa by I into Kf. Now tell me, how would you get this equation? You all know this equation. This formula, if you go through this formula, that stuff you know. Molar, instead of molarity, you can write number of moles by mass of solvent in kg, and number of moles you can write given mass by molar mass. Okay. Number of moles you can write given mass by molar mass. So see, this one is a given mass. This one is a molar mass of what? Solute. And this Wa is a molar mass of solvent or mass of solvent. Just put all the value. This value is 3. How this one is 3? Already given. Mb value is 58.545 for NaCl. This value is 1 kg because molarity, given number of moles solvent in kg. I value is 2. This one is 1.86. So 47.2 gram. Any doubt? This question is clear for all. Do you have any doubt? Question number 3. Calculate amount of CaCl2, where molar mass of CaCl2, which is 111 gram per mole, which must be added. Added to 500 gram of water. To lower its freezing point by 2 Kelvin. Assuming CaCl2 to be completely dissociated. Kf value is 1.86. Again, same thing. Solve it quickly. Giving you 4 minutes time. Quickly solve it. Completed. This one is again easy question, not a very tough question. Look, how can you solve this one? CaCl2 solid on aqueous phase. It becomes Ca2 plus aqueous plus 2Cl minus aqueous. Now alpha value is I minus 1, N minus 1. Okay. So what will be the I value? I value is basically this one is a 2, this one is a 1. So I value is 3. Okay. So I value is 3. Now you have to find out, calculate the amount of CaCl2. Again, you know this formula del TF, which is equals to I into Kf into M. Okay. This M you can write given mass by molar mass and number of moles by mass of solvent in kg. So just write down del, this one is a 2, this value is 3, 1.86. Instead of M you can write given mass by molar mass. Given mass, molar mass is 111 by solvent in kg. 500 gram means 0.5. Now find out the W value. 2 into 111 into 0.5. 3 into 1.86. 19.89 gram. Is it clear? Is it clear? Any doubt? Do you have any doubt regarding this part? This stuff is clear. Giving you last question for today. Try to solve it. Question number 4. 75.2 gram of phenol, that is C6H5OH, is dissolved in solvent. Solvent of Kf 14 Kelvin kg mole inverse. If depression in freezing point is 7K, find the percentage of phenol. Find the percentage of phenol that dimerizes. Dimerizes mean what will be the N value? N value, degree of dissociation you have to find. Dimerization case, how can you find the I value? I equals to the formula 1 minus 1, I minus 1, 1 minus N by 2. From here you can find the N value. Okay. Solve it quickly, giving you 5 minute time. Done. Look, in this case, first find out the MB value. Again, similar way, MB value KF into WB del TF into WA. Now KF value is 14. Just find out the MB value in this case. 14 into 75.2. This value is 7, and this one is a 1. So 150.4 gram per mole. Now what is the I value? How much mole dissipated? 94. Okay, dimerize. And this value is normal molar mass of phenol. What is the normal molar mass of phenol? That you have to check. And then I is basically normal molar mass of phenol. And this one is the observed value. That is 150.4. So 0.625. That is the I value. Now that is the I value. Now put this one. This value you know that. So degree of dissociation alpha equals to I value is 0.625 minus 1. 1 by 2 minus 1. Why 1 by 2? Because dimerization takes place. So after getting calculation, I value becomes 75%. Okay, is it clear? So that is about depression of freezing point. So relative lowering of vapor pressure, elevation of boiling point, depression of freezing point completed. Next class, tomorrow's class, I will do the osmotic pressure stuff. Osmotic pressure stuff, it will take little bit osmotic pressure stuff left, and the isotonic. What do you mean by isotonic solution? What do you mean by hypertonic, hypotonic solution? That stuff, right? So next class and Saturday's class, I will try to complete all the chapter. Only the azeotropic mixture part left, that I will do next to next class. Okay. Okay. Tomorrow I have a normal timing. That means 8 to 9 p.m. Okay. Okay. Then bye all. Take care. Bye.